Hello all, I'm Aaron, that's Mike, and we're going to give you an update on ArcFlash and PPE. So let's first start off with the definition of ArcFlash. ArcFlash is a release of heat and light produced when electrical current flows through an air gap between two conductors. Let's look at the structure of an arc flash. The first thing to happen is an arc fault. An arc fault is when the air gap between two high voltage conductors is compromised, allowing an arc to form, creating an electrical explosion. That electrical explosion is made up of two things, an arc flash and an arc blast. The release of heat and light is what's known as an arc flash. The release of high pressure waves is what's known as an arc blast. So, what are the consequences of an arc flash and an arc blast? Well, the temperatures of an arc flash can reach up to 35,000 degrees Fahrenheit. Putting that into perspective, that is about 3.5 times hotter than the surface of the sun. Being exposed to such high temperatures, it will burn the skin directly and cause clothing to catch on fire if not wearing the proper PPE. An arc flash can and does kill at distances up to 10 feet. And it's interesting to note that the majority of hospital admissions caused by electrical accidents are from arc flash burns and not from shocks. Subsequent to the arc flash is the arc blast. Now, the arc blast is the explosive expansion of both the surrounding air and metal in the arc path. During that arc, copper expands by a factor of 67,000 times, turning it from a solid to a vapor. This is very similar to an explosion caused by dynamite. Now, there are three dangers associated with this expansion. They are high pressure waves, sound, and shrapnel. The pressure waves can easily knock workers off ladders. The loud sound can rupture eardrums. And the metal that's expelled away from the arc can penetrate the human body. So there are two things that will cause an arc flash, a short circuit and a ground fault. Let's define these terms. A short circuit is when an energized conductor makes an unintentional contact with another energized conductor, as opposed to a ground fault where an energized conductor makes an unintentional contact with ground. The first picture shows an example of a short circuit creating an arc flash. A screwdriver is accidentally dropped between two phases, creating an arc. The second picture shows an example of a ground fault creating an arc flash. A screw is dropped in the electrical service, making contact between a phase and ground, creating that arc. Now, these are just two scenarios. There are several other events that will cause an arc flash, such as insulation breakdown, improper use of tools, corrosion, lack of preventative maintenance, and so on. Before we start talking about PPE, we need to know what incident energy is. Incident energy is the temperature produced in calories per centimeter squared at a certain distance from an arc flash. If you take a look at the first picture, if you were to hold your hand 1 inch over a lighter for 1 second, that is approximately 1 calorie per centimeter squared. It takes, and I really want to emphasize this, 1.2 calories per centimeter squared to create second-degree burns. Now I turn it over to Mr. Olivo.
PPE categories. Wearing the proper personal protective equipment will protect workers from the hazards of an arc flash. The 2015 NFPA 70E recognizes 4 different categories of PPE. Each category has a different arc rating it can protect you from. Looking at our fancy picture, these ranges begin at 4 calories per centimeter squared to 40 calories per centimeter squared. Now I want to note that these are the high end of the incident energies. I work better on the bottom, so I'm going to turn on my little. Can you hear me? Mic check. I'm going to take a step off this podium. Ooh, that was a big step. Sorry. So looking at PPE Category 4. PPE Category 4 actually begins at 25 calories per centimeter squared to 40 calories per centimeter squared. Category 3 begins at 8 calories per centimeter squared to 25 calories per centimeter squared. In TxDOT, we only have to worry about the first 2 categories, Category 1 and Category 2. Sorry, ladies and gentlemen, but the spacesuits in categories 3 and 4 will not make it into our fall fashion this year. So for PPE Category 1, its incident energy begins at 1.2 calories per centimeter squared to 4 calories per centimeter squared. So the ARC-rated clothing we need is long sleeve shirt, ARC-rated pants, ARC-rated coveralls, face shield, flash suit hood, jacket, parka, hard hat, safety glasses and goggles. We need to wear hearing protection with inserts, leather gloves, and electrically rated safety boots. When we move over to PPE Category 2, the incident energy raises from 4 calories per centimeter squared to 8 calories per centimeter squared. Everything else is pretty similar to Category 1. The main difference, looking at the picture, is we're going from a face shield to a full-on beekeeper. Well, sorry. But look at that guy, seriously. I mean, I want you to be protected. So you're going from a Category 1, which is 4 calories per centimeter squared, to 8 calories per centimeter squared. So if you do elect to wear a face shield, you have to remember that you have to wear it with the balaclava. Everything else is pretty similar. You still have to wear your ARC-rated long sleeve shirt, your pants, your coveralls, your hard hat, your safety goggles. Everything else is there. Now, you said everything is the same, correct? So if I have my long sleeve shirt and pants, am I protected? Well, if the incident energy is rated for the category you're in, yes. So if I'm wearing a PPE Category 1, I will not be protected for 2, but vice versa will be true. So if I have my PPE Category 2 PPE on, I can work in a Category 2 environment and a Category 1 environment. Just want to re-emphasize that. Does anyone notice that PPE Zero is not shown up here? While the 2015 NFPA 70 edition no longer recognizes Category Zero as an ArcFlash hazard, the need for it still remains. If incident energy is less than 1.2 calories per centimeter squared, we still have to wear the proper clothing. Now, what does this clothing consist of? Well, it consists of untreated cotton long sleeve shirt, untreated cotton pants. Notice I say untreated cotton and not ARC-rated cotton. And why am I talking about PPE Zero if the 2015 NFPA 70E does not recognize it? Well, TxDOT still recognizes PPE Zero. If you look at our online manuals, we still recognize PPE Zero. So we've discussed our 3 PPEs that we consider important, 0, 1, and 2. But the million-dollar question still remains. What level of PPE do we use? We're out there. Tell me, which one do I use? Well, here's the next part. 2 ways to evaluate ArcFlash. I know I'm passing around a book right now. It's the blue book, which is the NFPA 70E you hear me talk about. That's one way to decide the ArcFlash. The second way is to calculate the incident energy using ArcFlash study. We're going to go over both. Let's start off by using the table method. Table 130.7C15AA and Table 130.7C15AB. Mouthful, isn't it? Let's call them Table A and Table B for short. It'll be easier on all of us, I promise. So these tables will first decide, is PPE required? And if it is required, what level will be needed? And also the ArcFlash boundary that we would need to work in a safe environment. Table A. On the left-hand side of the table will be the task that we are performing. On the right-hand side of the table will be the equipment condition and the ArcFlash PPE needed for that task at hand. So say our preventative maintenance plan calls for us to check the operation of lights on a highway or traffic signal. So we go out there, we have to turn on and off some circuit breakers or flip on a hand-off auto switch. So our task would be the normal operation of a circuit breaker or turning off a switch. Now, if our equipment is properly installed, properly maintained, the doors are closed and secured, the equipment covers are in place, and there's no evidence of impending failure, then our table says no ArcFlash PPE is required. Now remember, we're looking at the 2015 NFPA 70E. But we're part of TxDOT. TxDOT still recognizes PPE of 0, so PPE of 0 will still be needed. Just want to re-emphasize that. Now say we're still looking at the same circuit breaker, and now the equipment is not properly installed. The equipment is not properly maintained. The doors are open or not secured, and the covers are off or not secured. Say you're in a type D service and the dead front is removed, or you're in a type A service and there is no dead front, or the evidence of impending failure. Say the circuit breakers are warm to the touch, or you open up the service door and the circuit breakers have tripped. Well, now ArcFlash PPE is required. So once you know that the PPE is required, what now? Well, now we got to go to table B to figure out what PPE is needed. Table B, I'm going to say this long one just so y'all can hear it one more time. 130.7C15AB. That's a mouthful, I'm telling you. On the left-hand side is the equipment. Tell you the equipment and the condition. On the right-hand side will be the ArcFlash PPE category and the ArcFlash boundary. So let's use that same example. Our circuit breaker's bad, we need to replace them. So say we were in a traffic signal, it's a 122 40-volt service. So our equipment will be panel board or other equipment rated 240 volts or below. The ArcFlash category would be 1, correct. The ArcFlash boundary will be 19 inches. So it tells us our PPE needed will be 1, boundary of 19 inches. Now let's take this next example. Say we move up to a 240, 480 volt service. So now our PPE category moves up to a 2, and the boundary moves up to 3 feet. Now this is very important. That means everyone within that 3-foot boundary has to wear the proper personal protective equipment, not just the person that's doing the work. So say I'm in there working on, the equipment, and the new guys over there looking, oh, what is Mike doing? He's working on this. I want to learn. Well, that person has to also wear the proper PPE. Mr. Aaron was talking about a line-to-line fault earlier, a line-to-ground fault. I'm working with my screwdriver. I drop the screwdriver. Boom! I want all of us to make it home safe to our families. Everyone has to wear the proper PPE, get home safe. This is important, folks. These labels that we make, we're going to talk about the second method. We actually put these labels on there. We do that with the incident analysis when we're running the software. We're going to put labels on the front of your electrical services, in front of your CTMS cabinets, in front of your hubs. This is why we do the calculations. This book method is just another way to actually do it if we don't have the time to do the incident analysis, or you haven't had the chance to run it. Mr. Aaron, he's going to take us through the start of how we did our pilot program and continue going.
Thank you. So currently TRF, we're doing a pilot where we're sending this form to districts to fill out the site information from the field, such as conductor sizes and breaker information. Then the districts send the information back to us, and we'll run our ArcFlash calculation software. And ultimately, like Michael said, we want to print out equipment labels and send them to the districts so they could put them on their equipment. The equipment label is going to show the incident energy at different buses and the PPE category to wear when servicing that particular electrical equipment. The picture here shows a form filled out by the Austin district for the traffic signal at US 290 and George Bush. So let's just do a quick walkthrough of the form. The first portion to be filled out is we need the city, location, GPS coordinates of the traffic signal. We need to know the transformer rating, conductor sizes, lengths, and type for the service drop and service entrance. Determine if the service drop is either overhead or underground. Second portion to be filled out, looking at the meter, we need the company, all the associated meter and barcodes. At the service, when looking at a circuit breaker, we need to know three things. Number one, what brand is it? Is it a Square D? Is it an Allen Bradley, GE, etc.? Number two, we need to know how many pole amps that circuit breaker is. And lastly, number three, we need to know what type of load that circuit breaker is feeding. Looking at the service information block, we need the manufacturer, service code, line voltage, data manufacturer. All that service information can be found on a label inside the panel. Third portion to be filled out, it's more of the same. The conductor sizes and lengths for the signal cabinet feeder, and the three things I mentioned for the circuit breaker on the last slide for the signal cabinet. Now, that information we ran in SKM, and the results show an incident energy of 3.4 calories per centimeter squared at the electrical service, and an incident energy of 0.1 calories per centimeter squared at the signal cabinet. In this real-world example, the textile worker will have to wear a Category 1 when servicing the electrical service. Or, if the worker is just troubleshooting the signal cabinet, he will have to wear a Category 0. Michael will continue with more examples.
So this intersection we calculated had a incident energy of 5.69 calories per centimeter square and a PPE level of 2 at the electrical service. The signal cabinet had an incident energy of 1.48 calories per centimeter squared and a PPE level 1 at the signal cabinet. At this intersection, we calculated a 1.72 calories per centimeter squared and a PPE level of 1 at the electrical service and a 0.34 calorie per centimeter squared incident energy at the signal cabinet with a PPE level of 0. And for this final intersection, we had a 0.71 calorie per centimeter squared at the service and a 0.36 calorie per centimeter squared at the signal cabinet. Both of these had PPE levels of 0. For all three of these locations, all of these were traffic signals, and all of them had similar configurations, but all of them had different incident energy values. All of them also had different PP&E values. Throughout this whole pilot program, Mr. Sidney Malloy, myself, Greg Jones, Aaron Ramirez, we were tasked with how can we make it safer? How can we encompass all of these services across the state and come up with one solution on how to bring this ArcFlash incident energy value and make the PPE level come down to 0. We want to just bring it down to 0. Is there a way to do that? And there was no discernible pattern to make that happen. We couldn't figure out, what worked, what didn't work, why are they all coming out different? So there's stuff that we could control and stuff we couldn't control. So we figured out, well, what can we control and what couldn't we control? Well, we figured out we can't control the transformer size of existing installations. We can't control the distance between the electrical service and the traffic signal controller. But we started looking into things that we could control. So we could control the size of the breakers and the size of conductors from the design phase. But will that actually help? So from a design perspective, we started doing research and trying to run calculations on actually doing designs of using these theories, reducing the breaker sizes and the conductor sizes. So I wanted to show you a couple of these examples. Using smaller breakers. So we took a traffic signal, and we normally run a 2-pole 70 breaker for the traffic signals. And the incident energy was 1.7 calories per centimeter squared, and we reduced it to a 2-pole 60. And the incident energy we found went from a 1.7 calorie per centimeter squared to 0.1 calorie per centimeter squared at the service, reducing the PPE level from a 1 to a 0. That's just changing the descriptive code. Simple. Same thing happened with illumination, going from a 2-pole 100 breaker to a 2-pole 60. We keep designing these systems for future, and especially for illumination. Oh, let's put a spare breaker in there. We're going to come back and add a couple other legs on this illumination. Or we're designing for HPS lighting when we're moving to the LED world, or incandescent lighting when we have LED circuits. Also for the breaker sizes for the 1-pole 50s, I know me and Mr. Henry were talking about it now. The 1-pole 50s we're trying to move them down to 1-pole 30s now. I mean, we measure intersections, and we're getting 5 amps out there, 5-6 amps. Okay, I turn on a vacuum cleaner, and what are we looking at? Maybe 22 amps? Say we don't want to violate UL in an existing service, and so we don't want to mess with something. So, but still, we have our maintenance crew going out there, and we want to make it safer for them to actually service the signal cabinet. So, changing the wire size might be something to do post installation. We know it works already doing it on the design phase, but say this is something on an existing installation. So we know it works on the design phase, but here's something that works on both existing and on a design state. So say you're going from the existing service to the signal cabinet, going from a number 4 to a number 8. You reduce the instant energy from 1.5 calories per centimeter squared to 0.5 calories per centimeter squared, reducing the PPE level from a 1 to a 0. I promise you, your maintenance crews and anyone going out there looking at that will be very happy going from wearing a face shield to wearing untreated cotton. I promise you that, being ARC rated to not having to worry about, losing the arm, they'll be happy. Reducing conductor size is reducing the incident energy, but is there anything else that can help with? These are just the rolling costs. It reduces money as well. There's cost savings. There's an 8.39% cost savings going from a 4 to a 6. A 4 to an 8 is a 17.87% cost savings. At the beginning of this, I was passing around a book. Who got my book and who got my conductors? Man, please take my conductors out of your purse. Don't be trying to sell my conductors. You got per diem for that. Don't be trying to buy a steak dinner or nothing. There's hidden costs involved with this. Theft deterrent. Anyone out here who works for TxDOT? I know a lot of us. Anyone dealing with theft of copper? A lot of us. I know Houston District does. Dallas, Corpus. I hear it when I was in traffic operations all the time. Oh, I want to bury my ground box. I want to concrete encase it. I want locking mechanisms. I want to put my ground box in the air. Well, that's not a ground box no more, but but the point is, everyone's trying to do something to try to reduce and mitigate copper theft. Smaller conductor size makes criminals less likely to steal it. Well, you're going from a thick wire, the size of my thumb, to maybe a thinner wire. And if it does get stolen, well, it's easier on the budget to replace. Just food for thought. Don't kill the messenger. To summarize, ArcFlash is the release of extreme heat and light. There's 2 ways to evaluate ArcFlash. The tables in the NFPA 70E are performing an ArcFlash study. Both of these will give us the answer we need, what levels of PPE was needed. ArcFlash hazard decreases when breakers and conductor sizes are reduced. The conductor sizes will also see a cost savings. But the main thing is PPE levels are needed and PPE needs to be purchased. And I know that you're going to ask this question, what do I need to buy? Where do I buy it? I want to direct all questions to that man right there. Mr. Sidney Malloy, raise your hand. Everyone call this guy, blow up his phone. He's the man with the plan. That's Mr. Sidney Malloy. But at this time, we'll open the floor to any questions. We'll answer to the best of our ability.
We have just one, please.
One
That's
question.
all we have for our time.
If
there are no questions, you can go to Sidney Malloy.
Just call him. He'll be all right.
Okay?